Welcome to Data Umbrella's webinar. I'm going to do a brief introduction. It'll be a few minutes, and then Laya will do a presentation, and we'll open it up. You can ask questions along the way, and this is being recorded. About Data Umbrella, we organize data science and open source events for the community, and we are a nonprofit organization. This is our team that makes it all happen behind the scenes. My name is Reshma. We also have Beryl, who contributes from Nairobi, Kenya, and Sangam from India. We have a code of conduct, and we thank you for helping to make this a friendly, welcoming community for all. Various ways to support Data Umbrella is if you could tell people in your network about Data Umbrella, that would be great. We also have our blog, our timestamps, our website is all on GitHub if you want to check it out and see if there's any issues that might interest you. We also are on every.org if you'd like to make a donation. We have a really, really rich library of open source Python R events for the community. And I'll share the link to the YouTube. If you don't subscribe yet, you may want to. We have a lot of playlists. One of them is career advice. Others include data visualization, contributing to open source, scikit-learn, Sprint, PyMC series, NumPy series. We also have a monthly newsletter at dataumbrella.substack.com. I will say we haven't been doing it monthly, so, but maybe every few months. So if you'd like to receive our newsletter, feel free to subscribe. I'll share it in the chat as well. We're on all these social media platforms. Meetup is the place for upcoming events. YouTube is where the videos are, our newsletter, and GitHub. And we're quite active on LinkedIn as well. This platform that we use is called Big Marker. And at the very top right, you'll see CC for closed captioning. So if you'd like a live transcript, just click on that and you'll be able to see it. Our upcoming events are in Meetup. We also have an online suggestion box. So if you're interested in speaking at a Data Umbrella event, or if you have a topic that you're interested in learning more about, let us know. Also, if you have any technical issues that you'd like to share with us or any other feedback, let us know. Today's talk is Analyzing Geospatial Forest Data with Geopandas and Rasterio. As a PhD candidate at Tarbiya Madaris University in Tehran, Laya's research interests lie in forest remote sensing and the assessment of forest ecosystem services. She's currently investigating the application of machine learning techniques to analyze multi-sensor remote sensing data, including LiDAR, radar, and optical imagery for the estimation of forest carbon stocks, biomass, and the provision of ecosystems services. Her research specifically utilizes GEDI, Global Ecosystem Dynamics Investigation. You can find Laya on LinkedIn and GitHub. And with that, I'm going to get started. So we seem to have, oh, Laya's there. Okay, Laya is there. Okay, Laya, I will let you pull up your slides. Is it just a little slow? Is that what's happening, Laya, with the slides?
Okay. My screen is shared, yes?
Yes, yes.
Thank you. Can I start?
Yes, yes, please begin.
Hello, everyone. Good morning. I'd like to thank the conference organizers for the opportunity to present my work. My name is Laya Zeinali. I'm a PhD candidate in forestry at Tarbiyat Madaris University, Tehran. Today I'll be presenting analyzing geospatial forest data with Geopandas and Rasterio. In this talk, I'd cover the motivation, methodology, key results, and conclusions. Let me briefly introduce my research background. Uh, if my internet is a poor connection, if I lost the webinar, please write in the chat. I see that. My research centered on a forest ecosystem, ecosystem services and carbon cycle, emphasizing the use of remote sensing, Python, and machine learning for forest modeling. This presentation covers the core components of my doctoral dissertation, which focuses on estimating forest biomass and carbon stock using integrated geospatial and machine learning approach to support sustainable forest management and climate change mitigations. Why is geospatial analysis considered a vital tool in environmental research, and what makes its applications particularly crucial for understanding, managing, and conserving forest ecosystem in the face of climate and land use challenges? Geospatial analysis is a powerful approach for understanding environmental and terrestrial processes. In forestry, it combines tools as GIS, remote sensing, LiDAR, and spatial modeling to monitor and manage forest ecosystem. This approach allows us to assess key forest characteristics including canopy height, forest cover, carbon storage, and biodiversity from local to global scales. By integration satellite imagery, uh, drone data, and field observations, geospatial forest analysis provides insights that traditional methods often overlook. In the face of growing challenges such as deforestation and habitat loss, it plays a crucial role in supporting effective conservation and sustainable forest management. Forest biomass and carbon is the essential topic in this research. Forest biomass is vital for both timber production and carbon storage, two vital ecosystem services. Forests store most of the planet's terrestrial carbon, playing a key role in regulating the global carbon cycle and mitigating climate regulation. Canopy height is one of the most important indicators for estimating above-ground biomass and carbon stock, and can be effectively monitored using remote sensing. Our study area is the Hyrcanian forest. Hyrcanian forest is stretching along the southern Caspian Sea, cover about 1.85 million hectares, around 15% of Iran's forest. It's an ancient ecosystem, and rich biodiversity, and they are among of the world's oldest temperate broadleaf forests, dating back to the uh, Tertiary period. Uh, the climate is a humid, temperate climate, and elevation up to 2,800 meters these forests has reached. biodiversity, including species like oriental beech, Persian ironpool, and yew, as well as endangered wildlife such as a Persian leopard. They are a vital role in carbon storage, soil and water protection, and climate regulation. However, deforestation, urbanization, and overgrazing remain major threats. Uh, these pictures captures by our team. Uh, these forests are now recognized as a UNESCO World Heritage Site. Thanks in part of the contributing of my dear Professor Dr. Hosseini, one of our leading experts in this field. Data that we used in this research. For these people, I utilize a diverse range of data sets, all of which were important, proceeded, and analyzing by the Python environment. The dataset include ground-based measurements and in Excel format for field data and radar imagery from Sentinel-1, optic imagery from Sentinel-2, LiDAR data from NASA's GEDI mission, as well as shapefile related to the study area, all of which played a fundamental role in the analysis. In addition, we had ancillary data like LULC, land cover land use map, and elevation data from SRTM that employed support the modeling process and enhance the interpretation of our results. An integrating approach to modeling forest canopy height and above ground biomass using GEDI, Sentinel-1, Sentinel-2, SRTM, and LULC data. Our research is two-phase. Phase 1, canopy height mapping, and Phase 2 is the biomass modeling. Canopy height mapping, we integrated Sentinel-2 and GEDI data along with the ancillary data with variable to generate forest canopy height maps. Then these forest canopy height maps, in addition the other data, for example, the all of my data, field plots, Sentinel-1, Sentinel-2, GEDI, LULC, SRTM are in the processes in the machine learning. Using machine learning algorithms, we modeled and produced final above ground maps for whole of this study area. Why we choose the Python? Python is a popular, free, and supported by a strong open source community. It offers powerful library like GDAL and Geopandas for geospatial analysis. Its simplicity and easy integration with software and as GIS, QGIS, ArcGIS make it ideal for automating and enhancing GIS workflow. Python offers multiple development environments such as Vital Studio Code, the Google Colab. We use the Google Colab Python code through there. However, within any setup, one of the primarily advantages of Google Colab is that it provides free access to cloud-based GPU and TPU, enabling the efficient processing of large data sets and machine learning without requiring high-end local hardware. I load these data in this environment. I don't need to download them in our hard. We selected Google Colab due to the seamless integration with Google Drive, and our maps saved in Google Drive. It's a good APIs that connect with Google Earth Engine, and this made it an ideal platforms for our project where we need to handle multi-source spatial data, performance complex remote sensing analysis, and develop machine learning. By using Google Colab, we could bypass the limitations of local memory. The environment allows us to call, process, and merge corrected datasets without the need to downloading or manual processing it. Especially when combined with the platforms like Colab, scientific research and geospatial modeling. The first stage of our work is called the libraries. That libraries I use to this research is a pandas, Geopandas, NumPy. That's all of these for them different purpose. Pandas for data cleaning, filtering, and tabular analysis. Geopandas extend pandas to work with geospatial data, vector data like the shapefiles. NumPy is a numerical operations and efficient array handling for my to this research it's for my field data that the Excel formats. Rasterio for reading, writing, and analysis raster data. GEE map for working with Google Earth Engine interactively in Python. The rest of the slide I explain about it. AirSpy simplify the common remote sensing and spatial analysis workflow. Scikit-learn for applying machine learning algorithms such as in this research the random forest. Matplotlib and Seaborn is good for visualization and plotting our data. Cartography for creating high quality maps and geospatial visualization. Fiona for reading and writing vector data formats used under the Geopandas. And Folium is the rest of the our research I explain about it. In this section, since we are importing data from Google Drive, we first need to connect Google Colab to the Google Drive. The data we import include the boundary of the study area, which is provided in a shapefile, SHP format, Sentinel-2 data along with vegetation indices and spatial LiDAR data that has already been combined. These datasets are variable in two formats: Excel table, raster image in TIFF. 3 data loaded and from Google Drive. After run this code, I reach to our study area map. This study area is 7th watershed out of the 95 watersheds here in Hyrcanian forest. As the number of 31 bands. Excuse me, our slides have 2 images, but don't show in this. How can I show these codes?
I'm not sure.
The code is below of this map.
Yeah, I'm not sure. I guess I would just keep going.
I can share my screen.
I can see the slides. I can see slide 13 on the screen right now.
Yes, I have in my screen. I share my screen, okay? It's okay?
Yes, yes.
Okay. I'm on the... These pictures, all of these pictures is for a Hyrcanian forest. Right? Oh, okay. Okay. I load these three data from Google Drive, and then I want to load our image for our data. That's it. Here, preparing dataset for modeling from these three data: Sentinel-2, GEDI data, and SRTM and LULC and vegetation indices. I create a data frame by Panda library. Our data set is 621 rows and 20 columns. These three items is from GEDI, and elevation slope is from the SRTM. As indicated by the columns header, this data frame contains information for Sentinel-2 GEDI used for masking forest area, just the forest area mask. The initial step in preparing the dataset for machine learning analysis involves partitioning in ratio training and testing. So it's a very important stage in the machine learning. Allege splitting data, we split data into 80% for training and 20% for testing. Some data set, especially big data, might include missing or NA values, so it's important to check them before we move to the next level that has any missing data in this research. Perform exploratory data analysis. EDA is an important step in understanding your data before building a machine learning model. To perform EDA on your training data set, we will use libraries such as Pandas for data manipulation and Matplotlib or Seaborn for data visualization. First, we will start by creating a data frame for the training dataset by Pandas and NumPy. These datasets created by these codes, these three is from the GEDI data, and other create a data frame in CSV format. Next, create box and density plus for the canopy height. Checking the data from all essential aspects, including normality, outliers, and overall consistency is crucial for reliable analysis. We also need to visually examine the data through plots, box plots, bar plots, and so on. That help us understand to distribution, detect outliers, and access data normality. In this case, the box plot here. In this case, the box plot show that the data distribution and dimension are acceptable for these data sets. As here, generate the bar plot show to mean the spectral reflectance for each bands. Here, as we can see the CCCI band contribution the most compared to the other spectral bands. CCCI is a vegetation indices that chlorophyll content index in the canopy height indicate the for me. We will visualize and distribution and potential outlier of each feature using box plot. The code will generate box plot for each features and showing the median outliers and any potential outliers. And this code we see the box plot of that's the bar plot previous slides. Then we see the CCCI is the very good data without any outliers. We will also visualize and distribution of each feature the target variable using density plot here and density plot for every features, for every bounds that's impact in our machine learning algorithm. Here we're checking for variable with low variance and possible outliers. If outliers make up more than about 5% of our data, they should be corrected or filtered out because they can reduce model accuracy. In our data is less than the 5% for each features and here show ours the number of the outliers that is good for these data sets. Select the train random forest. We will use the random forest which was introduced in scikit-learn. Scikit-learn is the library for machine learning algorithms. Here the random forest sets 42 is for the every turn the algorithm use the training data set, same training data set, and here I don't recognize any seeds and the rest of these we will use cufold cross-validation feature to split the training data into 10 subsets called folds. We can 5 subsets called it's for the time consuming 10 subsets but it's very high accuracy. And then check the RMSE score. The RMSE value, the RMS is an acceptable range in the reliable range, indicating that the model has performed well. In other words, the RMSE result suggested that the model provides reliable and accurate prediction. Finally, let's plot a graph showing the performance of random forest regression model predict using the test data and create a scatter plot. this chart and analysis results show strong performance and high accuracy. Here, regression line. Finally, we use the code to generate an output map. Here, the RMS is very good, and R2 is a very reliable. Finally, we use this code to generate an output map for canopy height. After that, the output is automatically saved to the Google Drive from this code. By this code, the output, the resulting map demonstrates high spatial accuracy area within this brighter tone represent region with denser forest canopy. Shapley, a popular explainable machine learning method, is based game theory introduced by Laya Shapley in 1953, which has been adapted for interpreting machine learning models. Shapley value provide a way to quantify each feature's contribution to a prediction by calculating its average marginal contributions across all possible subsets of features. In other words, Shapley values fairly distribute the credit for a prediction among different features, offering a comprehensive view of feature importance within machine learning. But this step is quite time-consuming. The entire analysis took approximately 21 hours to complete. Excuse me, my sound is okay?
Yes. I can hear you.
Okay, continue. These two, after estimation canopy height, the process is calculating forest biomass. For this purpose, a new notebook is created. The environmental is initialized by importing required libraries as the same library, and the analysis is carried out using the ground-based data. I install the libraries and then call them. Again, I'm preparing the environment, connect to the Google Drive. Then we call our field data in the Excel formats. Our field data is for NFI data. It's a very big data, but I need some columns from this data and call by this code call these columns from these data, and field data columns return an index object containing the columns names of the data frame. ToList converts that index into a standard Python list. Here we imported a large number of datasets and select only these columns. At this stage, Pandas library is very useful and efficiently handle and organize the data based on the field measurements. Here, that show ours the measurements, the volume of these forests, the biomass of these forests, and the canopy heights. the mean of the values. That's the biomass by field data is here, but I continue to receive the remote sensing data. Our field data include 2,553 rows and 128 columns. That's a very big data here. And as mentioned earlier, visualizing the data provides a clear insight into the trends. It also shows the R2 values here, R2 values, which indicate how well the model explained the variability in the data. It's acceptable and reliable. For volume, this code takes point data with UTM coordinate. It's very important. All of data and plot, field plot resamples in the same coordinate system. Our study area is two zones, 39 and 40. That WGS 84 system. First, it creates a geometry columns for the X and Y values representing each row as a point. Then it processes each zone separately by design the correct UTM coordinate system. Transfer the coordinate into WGS 84 and stores the results. After that, the transforms geodata frames are concatenated into a single dataset. Finally, the code extract the reprojected coordinate into new columns called longitude and latitude, allowing the dataset to be used directly in mapping applications or spatial analysis based on global geographic coordinates. This code is very important to accuracy our map. Here we call the volume library. Volume is a Python library that allows us to create interactive maps directly in Python, making it easy to visualize spatial data. The circle you see here, the map represents our plots. Here is a whole of our study area. The number appears to change when you zoom in or zoom out because the study area is large, contains many plots in the parts. Here, at this stage, we obtain the datasets and satellite imagery from Google Earth Engine catalogs. This process can be easily executed in Python by using our Google Earth Engine username and password along with corresponding code. Here, we can connect Python to GEE environment and access the data catalog directly. This part of the code is important because we define the geometry of the field data, setting the correct coordinate system here, ensure that we accurately extract satellite data for the same location in the subsequent step. Preparing field data include creating geometry from X and Y, assessing U-turn coordinate, and reprojection WGS84. Here is the same code for the resampled coordinate system. Here we called dataset ETH global canopy height. A 10-meter resolution global canopy height that built by machine learning, but by deep learning and Sentinel-2 images by ETH University. It's a meta map for creating for whole of the world. I call the EE library, then connect our Google Earth engine, then call these datasets from here. Then a mosaic canopy height image retain the correct spatial resolution and projection, which is essential for accurate geospatial analysis or overlaying with other datasets. It's a common and good practice in Google Earth Engine workflow when working with custom image collection and need to be standardized. And again, here the projection is a very important for the coordinate system. ETH cannot be height and matched with our data, the field data. And here, when combine all of these, our data sets reach to these rows and columns. Show here. Here we need the field data that in the CSV formats. The chart here define the file path from the dataset and call him, split and train again for these new datasets. The chart here represent the initial results of our workflow. Here, Arduino is a very acceptable and reliable overall trend and is consistent, but the model accuracy is still needed. The pre-processing and variation selections. This phase gave us a clear understanding of the baseline performance and guided our next step. Here we arrive at the key and exciting part of my work, GEDI data, which I'm particularly passionate about it. GEDI Global Ecosystem Dynamic Investigation is a spaceborne LiDAR mission launched by NASA, designed to provide detailed measurements for forest structure studies. GEDI produced a very large number of point measurements, so we apply quality filters and to return only a high quality data for our analysis. After the filtered the high quality data is remain in these areas. Here filter by quality and outlier again, and after this step, all of these data remove and the quality data remain in this here quality flag filter, and sensitivity filter. These two filters is very important for GEDI data, especially in this forest that's very steep slope, and the GEDI data is very challenge of it. And then add to map with these codes. This map is the GEDI data covered in my study area. Radar data, Sentinel-1. I call the Sentinel-1 and process with these codes. Calibrations, them, and UTM, projection to UTM, and other processing. And I import EE. I set our dates. These dates match with the field date measurements. And then we use polarization VV and VH for our studies, ascending, and we receive 110 images for our study area. And here a plot show of the Sentinel-1 for July 2023. The same step for the optical data, Sentinel-2. We import EE, set our dates, and these bonds from Sentinel-2 downloads and the processing filtered by cloud percentage is very important for Sentinel-2 data, and cleaned up cloud and covered by float for precision, rename for consistency, and finally the number of our image is 436 in my study area images. That's shown in plot in here. The blue vectors is our study area. Additionally, the Sentinel-2 bands, we need the vegetation indices. Are spectral metrics derived from satellites or airborne remote sensing data that provide a quantitative measure of vegetation conditions and dynamic. They are typically calculated by combining reflectance value from specific wavelength bands. Most commonly, the red and near-infrared region to capture the distinct spectral behavior of healthy vegetations, which absorb strongly in the red for photosynthesis and reflects highly in the near-infrared due to leaf structure. Through these mathematical transformation indices, such as the NDVI, Normalized Difference Vegetation Index, enable research to assess vegetation vigor, density, and stress level, as well as to monitor temporal change in biomass and ecosystem functions. Their simplicity, robustness, and strong ecological relevance have made vegetation indices fundamental tools in forest monitoring, agricultural, and environmental studies worldwide. In this research, we choose 5 vegetation indices that are important: NDVI and CCCI, and others. In the next step, generating maps and conducting the required analysis involve combining certain images and data sets. Since the process is highly specialized and time consuming. We will only provide a brief mention of it here and move forward without delving into the technical details. Here the composite of Sentinel-2 and GEDI bands in here, and create a data set from this composite. Then we create, after the created the data frame, we define feature and target variables here. These features and target is the RH95 from GEDI, and other is the predictions. Then splitting data in 70% training and 30% testing. Then train the random forest model is a very valuable algorithm. Excuse me. Here, the result of the random forest is R2 square, RMSE, and error. RMSE is very acceptable and reliable. R2 is okay for this research. Not very good. Then then we feature importance. Which of these features is importance for me? We need to know that. From these plots and that we create with matplotlib, NVI from Sentinel-2 is a very impact in our model. Here the code snippets evaluates the performance of the predictive model using multiple statistical methods. First, it calculates the coefficient of determination R2. Root mean square error RMSE, I say, and mean absolute error MAE to assess how well the predicted value match and observed ones. It also compute RMSE expressed as a percentage relative to both the data range and the mean target value, providing a normalized measure of error that facilitate comparison across different data sets. Finally, the results are organized into a data frame for clear presentation. Here the R2 score is a very acceptable for, and RMSE is a show the our model is a high accuracy, and error is a very good. Diagnostics data by matplotlib and Seaboard. Here we can observe the impact of refining data and optimizing some parts of the code. It's very important for these codes for the final accuracy. The graph shows a more stable pattern and the distributions of residual and here and compared with the previous steps. Here residuals is a very good. This means the model is starting and capture a relationship in the data more effectively. We also improved the parameters tuning and filtering the outliers, which contributing to better accuracy. The Hyrcanian forests are characterized by steep and complex soil, and to address these challenges and achieve more accurate estimating. We utilize SRTM data. Slope and aspect from SRTM data very help for our accuracy model. In this section, all datasets are merged together, including those derived from remote sensing imagery and the field-based data. All of my data obtained through forest inventory. They are integrating into a single data frame here. The columns header of which are presented here. All of this data sets to this data frame. Here to show the columns. In this slide, again, we clearly see further improvements in the model predictions. Model predictions ability. The scatter plot show a strong alignment between the predicted and observed value, indicating better model performance. The residual errors are smaller and more more evenly distributed here. Vegetation indices and topographic and vegetation indices, it demonstrates that the model is becoming more reliable and stable. Here we present the optimized and finalized version of our workflow. Colab combine our data in this table. This chart shows the tight clustering and predicted versus observed value, indicating very high model accuracy and the impact of every features in this table. The error metrics here. The error metrics are at their base level, showing that the data processing, variable selection, and model calibration here, model distribution and calibration successfully. Overall, the final analysis confirmed that the approach is robust and can be confidently applied for canopy height and biomass estimation in the Hyrcanian forest. And this graph. In this slide, we see two maps showing canopy cover and biomass, which is successfully generated for the entire study area in Python. This map is for canopy height, and this map is for biomass. The result demonstrates high accuracy and reliable across the region, our study area. To warm up in this presentation, I provide a brief overview of a full analytical process from data processing to modeling and validations. I use other machine learnings like XGBoost, KNN, and so on for this research that I couldn't explain here. I explain how each stage contributing to improving the model performance and accuracy. The outcome of this research have led to two Q1 journal articles, one of which has already been published. The final biomass map that's published in this article is a very high precision, and it's presented in one of those papers. The article is also available in my ResearchGate profile, and I would be very happy to discuss it further or share more details of anyone is interested. Please feel free to email me, and with any questions or collaboration, I'll be more than happy to help you. Finally, I would like to sincerely thank you for your time and for your giving me this opportunity to present my work today. Thanks a lot for your attention.
Hey, Laya, thank you so much for such a detailed presentation. Yeah, it was great. We don't have any questions in the chat yet. I'll just wait a couple of minutes, and we are at the top of the hour, so people may have to go. I had a question, which is, that's right, you'll share the slides, right? And then we can share them with that. I'll have the recording usually up within 24 hours. And your contact information is available on the last slide, so people can contact you. And also, would you also like be able to share that Colab notebook as well? Maybe that could also help people.
Colab notebook, I sent for you, yes?
Right. I mean to share publicly. Is that possible with the people who attended? Is that doable?
No, it's not public.
It's
not
okay.
complete, yes.
Okay, all right, that's fine. So we can share the slides, and thank you so much. I mean, it was like a very detailed presentation, and people benefit. And with that, I thank you everybody for attending. We'll get the recording up, and with that, I'm going to end the recording.